Okay, so now we're going to go over some of the properties of definite integrals. So the first one has to do with the order of integration. So if you have an integral that's going from b to a, f of x dx, then if you want to switch it back to negative a to b, you just multiply by a -1 out in front. So whenever you switch the limits of integration, put the bottom one on the top and the top on the bottom, it's equal to -1 times the limits the other way. So for an example, let's say you were just told, and you'll learn how to do this, that the integral from 1 to 2 of x dx was equal to 3/2. Then what this tells us is that the integral from 2 to 1 of x dx, if we just switch the 1 and the 2, this is equal to -3/2. Okay? The next rule tells us that if we have the integral from a to a, so the upper and the lower limits are exactly the same, of any function, then that's equal to 0. So for example, if you had the integral from 1 to 1 of x dx, that would just be 0. And if you think about what we said the integral means, right? So if we have some function, any function, f of x, and we're saying start at a and end at a, we want the integral under there. Well, if you're starting and ending at the same place, you have no width. So a straight line doesn't have any area. Okay, the next one says if you have the integral from a to b of a constant k times f of x dx, then that's equal to k. You can pull the k out, a to b f of x dx. So for example, if, we already said that the integral from 1 to 2 x dx equals 3/2. Then if we had the integral from 1 to 2 of, let's say, 5 x dx, we're saying we could pull that 5 out to the front. So this would be 5. We already said this integral was 3/2. So this would be equal to 15/2. And I don't exactly remember why, but my calculus teacher when I was first learning this called that outside the kiddie table, like when you're at Thanksgiving or whatever with family and all the kids have to sit at, and it said, think of constants like a kid, they have to go sit out at the kiddie table. So you can pull that constant out front. Okay, just like derivatives, the next one says if you're adding two functions in an integral, then you can break it up into two integrals and add them, as long and your limits would stay the same. So for example, we had the integral from 1 to 2 of x plus x squared dx. You could break that into the integral from 1 to 2 of x dx plus the integral from 1 to 2 of x squared dx. And you could evaluate both of those separately. Okay, the next one says if you have the integral from a to b f of x dx plus the integral from b to c of f of x dx, that's equal to the integral from a to c of f of x dx. So for example, if you had the integral from 1 to 2 of x dx plus the integral from 2 to 4 x dx, that's equal to the integral from 1 to 4. The important thing to notice is that these 2's are the same. Okay, and again, we can think about the picture we've talked about. Okay, so if this is our f of x, the integral from a to b, let's say this is a, this is b, and this is c. So the integral from a to b would be this area right here. So this, all of this area would be the integral from a to b f of x dx. And then the integral from b to c would be this area. And we're saying that adding those together, you could just do, so if you want all of that, we would want the integral from a all the way to c. Okay, so the next two are a little more confusing in words, and we honestly don't use them that much, but they give us good bounds on an integral. So we say if f of x has a maximum value, we just call that max f, and a minimum value, we call it min f. Then if you take the minimum times your b minus a, that has to be smaller than or equal to your integral, and your max times b minus a has to be bigger than or equal to. And this is another one that we can think about pictorially. So let's say our function does something like this just to make it dramatic. And let's say this is our a, and this is our b. So our minimum point is right here. And we're saying if you took that times b minus a, which would be the length. So think about when we talked about Riemann sums and rectangles. This would be kind of the smallest, if you were just using one rectangle, the smallest rectangle you could make, and that would give us a lower estimate, a lower bound. Okay, so that's what we're saying, this minimum value, that's what we're calling min f. So this rectangle right there is min f times the width here, which is b minus a. And we're saying that has to be less than or equal to our integral. Now, we're saying if we took the max point there, which we would call max f, and made a rectangle right there, it would be bigger than or equal to our integral. Here we see we get something much bigger. So that's why our integral has to be smaller than that. Okay. Then here we're talking about two functions. It says if f of x is greater than or equal to g of x on a to b, then the integral from a to b of f of x dx is greater than or equal to the integral of g of x. So again, we can think about the picture of this. So let's say this is our g of x, and our f of x is always above it. So if, let's just say this is a and this is b, well, this integral, right, would be this right here. And we're saying that if f is always above it, then the integral that you get there, the area under it, would be larger, okay? Now remember in another video we mentioned that if your function is below the x-axis, that counts as negative area. So this last part just says if your function is always positive, then you always have positive area. Your integral will be positive. Okay, so these are just some properties of the integral that you may find useful.